Welcome. In this video, we are going to go over another application of vectors. And as you can see, we have a diagram here and some text. So let's go ahead and just read the text and then discuss the diagram and set this up so we can solve this problem. So suppose a 100-pound load is suspended from a wooden beam by two chains as pictured. Compute the magnitude of the force each chain must be able to support. Now, we're making the assumption that the chains both make an angle of 45 degrees with the wooden beam. So let's add that new information here. So this is 45 degrees, and this is 45 degrees. We're also told that the load is 100 pounds. Now, we already have one vector sketched in. I'm going to go ahead and sketch in this vector here in blue, and then another vector here in purple. And let's just go ahead and call this vector L since it points to the left, and call this one vector R since it points to the right. And then for this bottom vector in red, I'm not going to use L again for load. I'll just use W for weight. And whoopsies, look at that. My 1 partially vanished. There we are. Hopefully it won't vanish again. Now, let's take into account the fact that this system is in equilibrium. That means that this load is stationary. The chains are stationary. Well, what that tells me is that L plus R plus W equals the 0 vector. Alternatively, we can write this as L plus R equals negative W. This is going to help us find the magnitude of each chain. Now, looking at this on an XY axis will help us find the components of each vector. So let's say this is our, there we are, this is our x-axis. And let's sketch a y-axis. There we are. Well, as usual, well, at least similarly to the other video, one of these vectors is really easy just to figure out by inspection. The W vector clearly has to equal 0, negative 100. Now, what about left and right? Well, now that we have our x and y axes sketched, I can include some other information here. That is, this angle here is 45 degrees, and this angle here is also 45 degrees. And it may be helpful to consider these as triangles. There we are. So these right triangles will help us find the x and y component of both the vector L and the vector R. As you can see, I moved that out of the way, so I can just write things down here as I need it. Highlighted is the x component of this vector. Well, using trig, we know that the cosine of this angle is equal to this adjacent over hypotenuse. And the hypotenuse has a length which is the magnitude of this vector. Rewriting that, we get the magnitude of this vector times cosine of 45 degrees. We can do something similar for the y component of this vector, which visually is this portion here. And this would be the magnitude of r times, not cosine, excuse me, sine of 45 degrees. Okay, let's do the same thing for vector L. So this is the x component there. And that's equal to the magnitude of L times, and actually I'm going to stop here really quickly, pause your video and see if we can figure out what we're multiplying by. All right, you should have attempted this independently now. And if you wrote times the cosine of 135 degrees, you're correct. If you don't see why, just remember in standard position on the xy plane, angles have their initial side along the positive x-axis and their terminal side would end here. So this is 135 degrees, not 45 degrees. And to make that really clear, I'll go ahead and sketch this in. This is 135 degrees. Now, of course, you could have used 45 degrees. You would have just had to have noted that we are in quadrant 2, so all the x components are negative. So alternatively, you could have written that this equals negative the magnitude of L times cosine of 45 degrees. And I'll write that down below. So now what about the y component of this L vector? That L component, excuse me, the y component of the L vector is the magnitude of L times sine of 135 degrees. And again, as I mentioned, alternatively, we could have written these as Lx equals negative the magnitude of L times cosine of 45 degrees, and Ly as the magnitude of L times sine of 45 degrees. Well, now that we have all of these components, we can finally set this up here. So I have the magnitude of L times cosine of 135 degrees, the magnitude of L times sine of 135 degrees. There's one vector. And I'm running out of space, so give me a moment to resize my screen. All right, there, so I resized my screen, and I also color-coded these, so we know that this is L in blue. And then to that, I'm going to add the R vector in purple. So this is the magnitude of R times cosine of 45 degrees. And then again, the magnitude of R times sine of 45 degrees. And let's see if I can squeeze this in. Well, what does that equal? Oh, I guess I'll do it on the next line. This equals, and now remember, this is the negative of W, so I know that it equals 0, 100. There we are. Well, now I can set up the individual components. So that is all the x's, all the x components, the magnitude of L times 135 degrees plus the magnitude of R times 45 degrees equals 0. I can also set up for the y components, and I'm going to leave some space below before you write the next equation. And you'll see why in a second. So I have the magnitude of L times sine of 135 degrees plus the magnitude of R times sine of 45 degrees equals 100. Okay, so right below this, I have the magnitude of L times negative root 2 over 2 plus the magnitude of R times root 2 over 2 is equal to 0. That tells me that negative L, or negative the magnitude of L, plus R, that is its magnitude, is equal to 0. Well, I can rewrite this as R's magnitude is equal to L's magnitude. Now let's pause real quick. Does this make sense? Well, looking at the diagram, it's clear that, yeah, these chains are definitely the same length, and they must be holding up the same force. All right, next, let's keep going. So here I have the magnitude of L times root 2 over 2 plus the magnitude of R times root 2 over 2 is equal to 100. And I can write this as the magnitude of L plus the magnitude of R is equal to 200 over root 2. Now, as you can see, I resized my screen just a bit since I was running out of space. And then on the side here, 200 root 2, let's take care of this real fast. Let's rationalize 200 root 2. Now multiplying by root 2 over root 2, that's 200 root 2 over 2, which is just 100 root 2. So on my next step, I'm going to do just that. I'm going to write this as the magnitude of L plus the magnitude of R equals 100 root 2. And now I can use this fact here, that these magnitudes are equal. So I'm going to write this as either 2 times the magnitude of L or 2 times the magnitude of R. It doesn't matter. I'm just going to choose R equals 100 times the square root of 2. So the magnitude of R is equal to 50 times the magnitude of root 2. Excuse me, I said that wrong. The magnitude of R is equal to 50 times the square root of 2. You can always tell when my mind is starting to wander as I make a video because I say the weirdest things. So if I say something that doesn't make sense, just assume my mind wandered and maybe shoot me a message, those of you in my class. Okay, so what does this work out to be? That tells me that the magnitude of R is equal to about, so it's approximately 70.7 pounds. And of course, this is also the magnitude of L. Let's go ahead and write out a conclusion. The magnitude of the force, each chain must be able to support is about, I'm going to round up here, about 71 pounds. All right, we are all done here. Please keep calm and math on.